In this lecture, let us try to understand how we can implement the list abstract data type using linked list in C. To give a quick recap of the list abstract data type definition, it is defined as an ordered collection of data items, and it can be represented as a collection of tuples t, I, where T is the data item having some data type. It can also be an abstract data type in its own right, with its own set of mathematical model and operations defined. And I is the ordinal or index, which can be used to define the order for all the elements inside the collection. And we also defined a set of operations that work upon the mathematical data model. Some of the operations were size, to give the number of elements in the collection or list; insert, to be able to insert an element E at an index on the collection; delete or remove, which can remove an element from the collection present at the index given as input; get element, which returns the element present at the given index; get index, it's like a reverse map which gets the index for a given element. Now let us try to recap the definition of linked list in C. It is a non-contiguous collection of data items. The meaning of non-contiguous is that the data items need not be present in contiguous locations in the memory. Two, each data item of linked list is present in a specialized structure called as node, which has two parts to it. The first part is the data item, and the second part is linked to the next node. This link is a pointer or address to the next node in the collection. This sequence can get arbitrarily long, and the last node of the sequence doesn't have a pointer to the node but has a specialized value called null to signify the end of the sequence. The third one, linked lists are useful to represent collections of arbitrary dynamic size, contrasting this to the limitation of an array which cannot support dynamically sized datasets, because the size of the array is fixed either in compile time or at runtime when the memory is first allocated. And now let us try to map the model of list to the linked list inside C. As we had seen, the element structure of a list takes the format t, I, where t is the value and I is the index. In linked list, the node can be roughly treated as an element which has a data part containing the element's value and an address part which points to the next node. Now, how do we map the index or the ordinal of the list abstract data type to a linked list? The index can be pointed to the distance between the node and a head of a linked list. So in this particular case, this node has a distance of 2 from the head. So we can consider that this node has an index of 2. So the value of the element of the abstract data types model maps to the value of the node of a linked list, and the ordinal of the element of abstract data type can be thought of as being equivalent to the distance of the node from the head of the linked list. So the first node that's connected to the head has an index of 1. The second node, which is connected to the first node, has an index of 2, and so on. Here is a structure in which I store the node contents. So I have a value which stores the data item, and then I have a pointer to the next node defined as a second element of the structure. So this structure can be diagrammatically represented as having two components. One is value, and the other is the next pointer that points to the next node, and so on. Now, to make my life a little bit easier, I've also defined another pointer called head, which points to the first node of the linked list. to make my life a little bit more easier, I've also defined another structure called as list that has one member, which is nothing but the head of the linked list. And here is the API that I defined representing the operations of the list abstract data type. Most of these operations are pretty much self-explanatory from their names. The operations of first, last are specialized versions of get. First is get of 0 and last is get of the size of the list, and append is something that inserts the element at the end of the list. Here are some of the utility functions that I've written to help me with some bookkeeping tasks. Print is used to print out all the elements of the linked list. Linked list iteration is a code that is repeatedly used in lots of methods defined for a list abstract type. In a generic form, the iteration of the linked list starts from the head and follows the next pointers of the nodes of the linked list and terminates at the node which doesn't have the next pointer set. Print prints out the value of each of the node as it does the traversal. New node is a help function that is used to allocate memory and create a node by assigning the input element to the data part of the node and setting the pointer to null. The functions that call new node will have to take care of assigning the pointer to an appropriate node. New list is another helper function that allocates memory to the list structure which contains a head, which in turn maps points to the linked list structure. You might have a question as to why we have this additional list structure that in turn has the head of the linked list. The reason why I have this is that for all the methods that have to modify the pointer head, we have to pass a double pointer in order for us to be able to change the content of this head. Because whenever you pass a pointer to a method, a copy is made of the pointer data type inside the method. When a copy is made, you can't change the value of the original pointer, but instead the value that you've changed will be restricted to the local variable pointer that is used for copying the original pointer. So normally in such cases, what we have to do is to create a double pointer, which is nothing but another pointer variable that points to the pointer that you want to modify. And when you pass this value into your method, you can then access this original head and change its value. So to avoid having to pass a double pointer, I have a list structure defined that will contain the head. And I can just pass the pointer to the list structure, and I can have access to the head that is defined in the main function from all of the functions which manipulate the linked list. Now let us take a look at the insert function that tries to insert an element at the given index into the list L. The first part of the code is to verify that index is within the bounds that we expect it to be in. Index cannot be less than 0 and it cannot be greater than the size of the list. So if you take a list, this is 0 and this is size of the list -1, because indexes in arrays or any other data structure in C start with a 0, and we are trying to mimic the same semantics here in our linked list implementation as well. So you can insert an element only between 0 and size L, and any other value is invalid and is summarily rejected. This is the first piece of code, which is nothing but the range check of the index. This part of code gets a new node created from the helper function that I was talking about before. This particular piece of code handles a special case where the list is currently empty. So in this particular case, you have a list which maps to a head, which in turn is not pointing to any list. So in this particular case, we would want the head to just point to the new node that has been created by us. So this is removed, and then we associate a new node to the head. Now you see the reason why I just created a pointer, additional pointer to put my head of the linked list. This operation would not have been possible without having to pass a double pointer, because when you pass just the head, which is nothing but a single pointer, it would create a copy of pointer in this method, and it would modify just the local copy to point to the new node. And the original head that this method receives, or the original head that the caller of this function would have, is untouched, and it would still point null. This part of the code is to traverse through the list till the node with index I is reached. So this traversal, as I said, is pretty common in all the methods. So you have a list which has a head, which then has the linked list. So start with attempt, and then essentially traverse using the next pointers, at the same time incrementing a temporary variable I as you move along the nodes. So I is initialized to 0 here, and then it's incremented by 1, 2, 3, and so on. So this iteration would stop as soon as I reaches the value of the index. So if index is given as 2, I would stop after it reaches the second node. Remember, we are talking about indexes which are 0 based. So the first index is 0, second index is 1, third index is 2, so on. So this iteration starts with the head, and then the variable I is incremented as we traverse along the list. This statement temp equals to temp next is the one that allows us to traverse through the next pointers, and it stops as soon as temp reaches the node which we want to insert our new node in. And then finally we have this code which inserts the node after the current temp node. So if this is our temp node, this was originally might have been originally pointing to another node. So what we do is, as a way of pointer manipulation, we just point new node to the old temp nodes next. That is what this statement does, and then we assign temp nodes next to point to the new node, and this later gets invalid. So this basically sandwiches the new node between the temp node and the next node of the temp node. And this special case is to handle a scenario where you would again have to change your head, because you're trying to insert your node at the 0th index. So in that case, all you have to do is, so this is your temp node in that case. What you have to do is to point your new nodes next to the temp node, and then your list's head to the new node. Again, this is the reason why we created a structure of list and then have a head in it. Otherwise, changing the head from the method would have required us to use a double pointer. So let us try to see how delete is implemented. This is the standard index range check that we normally do for the validation of input index. For deletion, one thing that we need to note is that instead of having a single pointer temp that would be used to iterate through the linked list, we also have another node called previous that will be one step before temp to aid us in deleting the node. To illustrate this point, so let's take a linked list which points to head, which in turn points to the actual nodes. Initially the temp points to the first node or 0th node. You have previous node as null, which is basically set up by this step. And whenever temp moves one step, previous would follow the temporary pointer. So if temp moves one step more, you have previous move from. The previous essentially follows temp and is behind temp by one step. Now, why is this needed? This is needed because if you want to delete this particular node, you not only need access to this node, but also need access to the previous node so that you are able to change the pointer of the previous node to the temp node's next node. So to allow us to do this operation seamlessly, we have to maintain 2 pointers. And this operation is a standard iteration that traverses through the linked list structure till the node with the input index is reached before deletion is done. This is to preserve the value, to return the value to the caller that's being deleted. And at the end, we adjust the pointers, and there are 2 cases that we need to consider. The first case is where list, which points to the head, which then points to the nodes. The first case is where the temp is pointing to the 0th node and the previous is null, which means you're deleting the 0th node. In that case, all you need to do is to point your head to the temp nodes next before destroying this node. This is handled by this case, and this is the normal regular case where you're deleting a node that's in the middle. So you have your list, you have your head, and then you have your actual nodes. Let's say you're deleting this node, which is in the middle of the linked list. Your previous pointer would be pointing to this, and your temp pointer would be pointing to this node. So what you have to do is to point the previous is next to the temp's next, which is what this statement exactly does. And then at the end of it all, you can just free your temp. So your new structure will be the head pointing to the next node, and this will be your next node.